Have we pressed record? Great. So today's topic is gravity. Now, gravity is one of the fundamental forces that makes the universe work the way that it does. So we've got these four forces. Gravity is one of them. It's the one that's going to be sort of most relevant to your daily life and experience. And it is a property of matter. So matter is anything that has mass and takes up space. Now each of you has mass. We could weigh you in something like kilograms, figure out how much stuff makes you up. Matter is kind of just a fancy sciencey word for stuff, right? You all have mass. You all take up space, and that means you matter. There's the look from Anaya that I was expecting. I knew that I was going to get that look at the start of this class, and I was ready to appreciate it fully. All right, so all of you are made of matter. That means that all of you both have and are affected by gravity. Gravity is a thing that is intrinsic to matter, to stuff. All of the stuff in the universe is attracted to all of the other stuff in the universe. This is not just something that pulls you towards the Earth. The Earth happens to be the biggest source of gravity nearby, and so when you think about gravity, you mostly think about the force of gravity pulling you towards the Earth. But in reality, all matter in the universe is pulling on all other matter. All of you, we said, are matter, right? And that means that at a fundamental level, baked into the fabric of the universe, there is a force of attraction between you and every single other person in this classroom, and indeed between you and every single person on this planet. And that's not just because y'all are going through puberty. Look, every time, every bad pun is going to get this reaction, and I will relish each and every one of them. So, gravity is a force of attraction. There are things that make that force stronger or weaker, right? We mostly don't worry about your matter being pulled towards your classmates' matter because, they just don't have that much mass to them, right? At least in comparison to something like the planet. So the planet is this really big, really close source of mass. And it turns out that those two things, how massive you are and how nearby you are the two things that impact how strong the force of gravity is. So how strong gravity is mass and proximity. Yes, Joaquin?
So if there was a bigger planet that was close to it, if the moon was a lot bigger than the Earth, would we get pulled towards the moon?
If the moon was a lot bigger than the Earth, it really depends on how close we were to the moon versus how close we are to the Earth. For example, Jupiter is way bigger than the Earth, right?
It's so far.
But it's really far away.
Yeah.
So you can go outside, get a telescope, and see, oh, that's Jupiter up there, right? But you don't fall towards it, even though Jupiter is way more massive than the Earth is. Because even though Jupiter has more mass, it's way more distant. And of those two things, mass and proximity, the one that actually matters more is proximity. Yeah. All right. Next little bit of stuff that I need to make sure y'all understand is kind of one of those frustrating things. Physicists like to take words in English and give them slightly different meanings in physics English. In English, mass and weight mean the exact same thing. It's just like, how heavy is this thing? How much stuff is there? In physics, that is not true. So in this particular dialect that we use when we're talking about physics specifically, mass and weight actually have very different meanings. In the same way that velocity and acceleration have different meanings. And it's really important to be able to tell the difference between them, because sometimes you might have a formula that has both acceleration and velocity. So we have to keep these ideas separate in our head. Mass and weight are not the same things. What mass is a measure of how much matter, and matter is just a fancy science word for stuff, how much stuff makes you up. Literally how many atoms and molecules are in you. That's your mass. Okay? We measure mass using kilograms. And the abbreviation for mass is a lowercase m. Yes, Shay?
Got my water bottle?
Yes, you may go grab water.
I know, fill it up.
Oh yeah, absolutely. You can just use the sinks at the back of the classroom. So, we use a lowercase m to mean mass, and yes, that is frustrating because the lowercase m can also mean lots of different things depending on where it is in context. So you have to pay attention to the context of things. If it's in a formula, like we haven't gotten to this yet, but eventually we'll learn a formula that's F equals m times a. Force equals mass times acceleration. In this example, that lowercase m means mass. But if I tell you that if you see like 30m, here, this m means meters. Because it's next to a number, so that must be a unit. However, if you see something written as like 30 mg, well now this m is a prefix that means thousandths of a gram. So here that means milli. And yes, it is frustrating that depending on context, the same letter can have different meanings, but it is important to know. So we measure it in kilograms, that's the unit. And the abbreviation for the concept of mass is a lowercase m. That's how much stuff makes you up. Literally how many atoms and molecules are in you, or in any object. Weight is slightly different. It's connected. It's very closely connected. There's a direct correlation. The more mass you have, the more weight you have. But they are not the same thing, because what weight actually means is weight is the force of gravity pulling on an object. So weight is how much gravity is pulling on your mass. We measure weight in a unit called newtons. It's named after Sir Isaac Newton. And the symbol I would use in a formula to represent weight, well, weight is the force of gravity pulling on you. So gravity is a force. We use a capital F to mean force. And then we stick a lowercase g next to that to say, hey, this is specifically the force of gravity that we're talking about, not just any force. So mass is how much stuff there is. Weight is how much gravity pulls on that stuff. If I were to take you and teleport you to the moon, you are still made of the same amount of muscle and bone and blood. Your mass is unchanged, whether you are on this planet or on the moon. However, your weight would be very different, because the moon only has about 1/6 of the Earth's mass, so the force of gravity, that attraction between you and the moon, is only about 1/6 as much. So, on Earth, I have a weight of about 175 pounds. Right, so that's my weight on Earth. That's how much the Earth, this planet, pulls on me. On the moon, I have a weight of like 29 pounds. But I'm still made of the same amount of mass. Still amount of matter and bone and blood and hair and teeth. Right? All of that is still there. I'm sorry, did I make it gross? Gabby, you just gave me a look like, you're not supposed to mention teeth. Same amount of stuff makes me up, regardless of where I am. So my mass is unchanged, but my weight is different, because weight is how much gravity pulls on that mass. Now, it is worth noting, these things are connected, because mass is one of the things that impacts how strong the force of gravity is. So if I have more mass, the force of the pull on that mass will be bigger. Gravity is a property of matter, so the more matter there is, the more that force of attraction is. Now, at the same time, gravity gets stronger the closer an object is. So we already covered this whole idea of like, hey, why don't I fall towards Jupiter? If I walk outside right now, I can go stare at the sun. Don't do that, don't stare at the sun. I could stare at the sun, but I'm not falling up directly towards it, even though the sun is way more massive than the Earth is. And the reason is because the Earth is closer. So that's the thing that I'm falling towards. I don't fall towards Jupiter because it's so far away that the force of gravity between me and Jupiter is much weaker than the force of gravity between me and the Earth. Yes, Talia?
As far as we know, is Earth the planet with the strongest gravitational pull?
It is the planet with the strongest gravitational pull on you right now. It's not the planet with the strongest gravitational pull in general. I'm not going to make you learn the universal gravity equation, but in that equation, there's a couple things that go into it. The mass of the two objects you're talking about, so like your mass goes in, the mass of the Earth, or the mass of Jupiter, or the mass of the Sun, whatever the second object is, goes into that equation. And it's divided by the distance squared. So the distance also goes in, but distance actually makes a much bigger impact than mass does. So how big the force of attraction is between any two objects is something that we could calculate. And it's going to vary depending on how far apart things are, right? And it's going to vary depending on how massive these two objects are. Now, and from that we can basically figure out like, hey, how much is gravity going to make an object accelerate? Because remember, gravity is a force, and what a force is a push or a pull that can cause an object to accelerate. So the whole point of gravity is it makes things speed up, right? If you step off a table right now or hop off one of these chairs, you're going to start accelerating downwards. You're going to speed up in a downwards direction because gravity is making you accelerate. Everyone okay so far with this? Do we need any pauses? Any questions? Any clarifications? Raphael.
How do magnets work?
How do magnets work? Magnetism is a different one of these forces, right? It is a force of attraction. There are some similarities between magnets and gravity. For example, both magnets and gravity get weaker the farther apart things are. Magnetism and gravity have some things that are different. Magnetism could be a push or a pull. Gravity is always a pull. So gravity always pulls things together, whereas magnetism can either pull things together or push things apart. We'll talk later on in the year about what some of the causes of gravity are, but the very short version is that all matter is made out of atoms, and all atoms have electrons, and electrons spin. And electrons can either spin in the same direction or different directions. And every time an electron is spinning, it generates a tiny magnetic field. And if you have a bunch of electrons that are spinning in the same direction, then those magnetic fields add up instead of canceling out. And that can create like zones in a material that we call magnetic domains. And when those magnetic domains are all facing the same direction so that the force of magnetism can add up instead of canceling out, you can have a magnet. And those magnets only pull on certain objects, namely the objects that have electrons that are all spinning in the same direction. So that's the like very short version of how do magnets work. But that was like a 1 minute explanation, so it's a big oversimplification. We'll get into magnets in the spring.
This magnet came out in this video.
Oh yeah, that happens, if the felt comes off. Try not to, I know there's a temptation to sort of pick at that, but try not to pick at that because once you pull that off, the magnet's gone and they kind of break. Let's go to Shep.
If the sun was like right next to Earth, like as close to the moon was to Earth, would we get pulled towards that because it's
Yes,
so much bigger?
for sure. And in a very real way, we are actually falling towards the sun.
Yeah.
An orbit is just falling towards something and missing.
How about like Jupiter, if it was as close as the moon?
If Jupiter was as close as the moon, we would crash into Jupiter. Absolutely. Or, depending on how much forwards velocity we have, we could end up in an orbit around Jupiter. Certainly Jupiter has many moons.
So we become one of Jupiter's moons?
Yeah.
That'd be kind of sick.
That'd be cool.
We could like see the gas. That'd be
See the
sick.
big spot now? Yeah, Joaquin?
Would magnets work differently underwater? Like would they move slower?
Certainly objects moving towards each other would have to like move through the water, so there'd be more drag. But I don't believe that water would change a magnetic field, but I'm not an expert in that, so I could be wrong. I think it should work regardless, in the same way. It shouldn't make the magnetic field any weaker. All right, back to gravity though. Magnetism is another force. And just as we use Fg for gravity, I will just go ahead, since it came up, I would use Fm to talk about magnetism. All right. Y'all probably think of gravity as the force that pulls you down to the earth, but really it is a mutual attraction between you and the earth. So my weight, which is to say the force of gravity between me and the earth, is 175 pounds. That means that the Earth is pulling on me with 175 pounds of force, but it also means that I'm pulling on the Earth with 175 pounds of force. It's mutual, right? Equal in strength and opposite in direction. Now, 175 pounds of force, that is enough to make me accelerate. However, it is not enough to make the Earth accelerate in any meaningful way. Why? Because the Earth has a whole bunch of mass. And gravity is not the only property of matter that we've got. So gravity is a property of matter. More matter means a bigger force of gravity on objects. But inertia is also a property of matter. And inertia is a tendency of an object to keep doing whatever the heck it's doing. So something that's stationary wants to stay stationary. Something that's moving wants to stay moving. The Earth, in its orbit around the sun, wants to just continue its orbit around the sun. Right? And the more inertia an object has, the bigger a force it takes to make that object speed up or slow down or change direction. The bigger the force you need to make something accelerate. So we have this really interesting thing that goes on with gravity. Gravity is pulling on me with a bigger force than it's pulling on any of y'all, because I have more mass than any of y'all. At the same time, though, it takes a bigger force to make me accelerate than it takes to make you accelerate. Imagine like two people running at you, like a linebacker in the NFL. So like a big, burly, fat dude with a lot of mass, right? And he's running at you versus like a fifth grader running directly at you. Can you stop a fifth grader in their tracks that's running at you, probably?
No.
Very strong.
Something good is
Maybe, like probably you could stop a fifth grader. But you're not going to stop somebody who's got way more mass than you, right? Because it takes a lot of force to make that person slow down, or speed up, or change direction. Gravity pulls on me with more force than it pulls on you. But it takes more force to make me actually move. It takes more force to change my acceleration. And those two things actually end up perfectly canceling each other out. The fact that there is a bigger force pulling on me, and that it takes more force to pull on me and make me speed up. And what that actually results in is if there are objects that are falling, gravity makes them accelerate exactly the same amount, regardless of their mass. On Earth, if the only force acting on an object is gravity, then that object, if you drop it, is going to accelerate at a rate of 9.80 meters per second every second. So that means that every second that goes by, it's speeding up by 9.80 or about 10 meters per second. So let me write that down. I would write this as acceleration due to gravity. So A for acceleration, a G to show I'm talking about gravity. So acceleration due to gravity is 9.80 meters per second every second. And remember what we said about acceleration. You should think of this as existing in two separate parts. So basically, every second that goes by, we're adding 9.80 meters per second to our velocity. So that top part, this is how much our velocity is changing. That's our delta V. And this bottom part, a second, is how often that change occurs. For our class, I'm going to make a note. This number is really close to 10. So if you want to round that and just say 10 meters per second, you are absolutely welcome to think of it like that. And what this means is that if an object is falling, every second that goes by, it's speeding up by about 10 meters per second. If an object has been thrown up, then every second that goes by, it's slowing down by 10 meters per second. And it'll slow down until it hits 0 meters per second, until it's stationary. And then it'll keep accelerating in the downwards direction and it'll start speeding up. So if you've ever been on the swings, you know that moment when you're right at the height of your swings? You actually stop. There's a moment when your velocity is 0. And then you speed up, right? You're fastest when you're at the very bottom. And then you're slowing down again as you go up. So it's like you're speeding up, and then you slow down as you're moving on the upswing. How are we feeling so far about this? See a lot of thumbs up. Good.
Go.
All right. I want
No reaction.
to take a moment and delve a little deeper into this thing I said about all objects accelerating at the same specific rate. Because what makes this tricky for folks is the fact that that's not what you observe in your daily life, right? If I take a piece of paper and a textbook and I drop these, they're not going to fall at the same rate. Which one's going to hit the ground first? The book's going to hit the ground first. Right? That's not terribly confusing.
It's got a lot of mass.
The reason why is not because gravity makes this book fall faster than the paper. Any ideas what the reason why is? Yossi?
Its mass does or its weight?
It's actually not because of its weight. Although its mass does sort of come into play in that this has more inertia than this does. Talia, any ideas?
Is it like the air?
It's the air. There's more than one force in play if I drop this. There's gravity making it speed up, and then there's air resistance slowing it down. Air resistance is caused by like all of the molecules and particles of air that this object has to push out of the way as it falls. And gravity makes all objects accelerate at the same rate, 9.80 meters per second, regardless of their mass. Mass cancels out of the gravity equations. Mass doesn't cancel out of air resistance. So it's easier for air resistance to slow down something lightweight than it is for it to slow down something heavy. So it's really just air resistance that makes the difference here. Yes, Joaquin?
So theoretically, if someone made a room that had no air resistance and they dropped those two, they would hit the ground at the same time.
Why, yes, and in fact, that is exactly what we're about to demo, so let's pause and watch this video.
Spoiled it. My bad.
So here we have a NASA facility in Ohio.
This is NASA's
And they're gonna
Space
pump out
Power
the air.
Facility in Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built out a concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
So this first drop is just a normal drop. We still have air.
Galileo's
We still have
experiment
air
was
resistance.
simple. He took a heavy object and a light one, and dropped them at the same time to see which fell fastest.
What's the red?
Bowling ball. So no big surprises there. The ball falls faster than the feathers. That's
In this
with air
case,
resistance.
the feathers fell to the ground at a slower rate than the bowling ball because of air resistance.
Wow, they read exactly where it falls.
So, in order to see the true nature of gravity, we have to remove the air.
So they're going to close this up. He's leaving the room, don't worry. They're pumping all of the air out of this room.
I wanted to see what happens.
So there's not going to be any force in play except for gravity.
If he went in there, what would happen?
It
He
takes
would
3
suffocate
hours to
them.
pump out the 800,000 cubic feet of air in the chamber. There are 2
Would
laboratories,
it happen like
but
this?
once it's complete,
So you would
there's
just
a near perfect
Stop.
vacuum inside.
610410, Station 1, go for drive. 30 days, 1, pressure set.
This was auto-safety.
all right. Watch this. This is going to be in slow motion.
8, 7, 6, 5, 4, and 1, 2, 1, release.
So no notice the two objects falling together. I also want you to notice that the rate at which they're falling, their velocity is changing. At first, they're moving pretty slowly, right? As time goes on, every second that goes by, they're covering more meters per second. Like the velocity is increasing. We're going more meters every second as time goes on. Much faster when it hits the ground than when it started. But they hit together at the exact same time.
They came down exactly the same.
Exactly the same. Exactly the same.
Those don't move nothing.
That's just brilliant.
Isaac Newton was saying that the ball and the feather fall because there's a force pulling them down. Gravity.
All right, we're going to stop there with this. So, this is all very well to be like, oh, well, NASA's got a big fancy facility, and at the NASA facility, we could remove all the air and see this. But we do not need a big fancy NASA facility to prove this. We can use some books and paper. For this bit, y'all might need to take that in hand because you are going to want to be able to see me and also the ground. But keep it horizontal. We don't want to go vertical. So, textbook versus a piece of paper. Air resistance is in play. The paper's going to hit air on the way down. Which of these is going to hit the ground first?
Textbook.
Textbook, absolutely. That's exactly what happens. Textbook hits first. Air resistance slows this paper down considerably. Now, this does not happen because the paper is lightweight. And I can show that really easily just by changing the profile of the paper. If I crumple the paper up, now it is going to hit less air on the way down. So we can dramatically reduce the amount of air resistance. There is still going to be some air resistance on both objects. And because this has less mass, it has less inertia, so it's a little easier for air resistance to slow this object down. So this probably won't be exactly even, but it should be pretty close. Y'all ready?
Yeah. Whoa.
Pretty close.
Yeah.
I can do better.
Nice.
I can make it so not a single molecule of air actually hits this piece of paper on the way down. I can completely eliminate air resistance. And that would mean that these objects hit exactly together.
Suck out the oxygen.
I'm not going to suck the oxygen out of the room
Oh,
because
you
I would
suck
like
it.
all of you to survive.
Yeah.
But what I can do is simply put the paper on top of the book, because now the book's going to move all the air out of the way.
Oh yeah.
Right? So this piece of paper, if it was actually about gravity, if gravity was somehow less effective on the paper than it was on the book, then you would see the paper sort of be left behind. But that's not what's going to happen. These two things are going to fall together because gravity makes both of them accelerate at the same rate. When they first leave my hands, they're at 0 meters per second. Every second that they fall, their velocity is increasing by 9.80, or about 10 meters per second. All right, y'all ready? Whoa. Perfectly together. Perfectly together. Because gravity makes objects accelerate at the same rate. The force is stronger on the book than on the paper. But it also takes more force to accelerate the book than it takes to accelerate the paper. And so at the end of the day, both these objects accelerate the same amount. If it's only gravity. Any questions about gravity so far? All right, let's do a quick review of what we've learned today. So here's our key concepts. These are the things I want to make sure that y'all actually have down after today's lesson. Gravity is a fundamental property of matter, like inertia. The more mass something has, the more gravity it has. It is a force of attraction, not just that pulls you towards the Earth, but between all matter in the universe. It's a mutual pull. It's not just that the Earth pulls on you, you also pull on the Earth. Not only Does the Earth pull on the moon? But the moon pulls on the Earth too. That's why we have things like tides. It's literally the water on our planet is moved towards the side of the planet that the moon is on. That's what causes high tides. Yes.
Gravity is a fundamental what?
It is a fundamental force, and it is a property of matter. There's two things that affect how strong gravity is: mass and distance. Gravity is stronger, the force of gravity is stronger if there's more mass, and the force of gravity is stronger if things are closer together. Joaquin.
Wait, so that means that like when to determine high tide and low tide is when that part of the water is closest to the moon?
Yeah, so here, let me give you a picture to help with this. There's actually a really complicated thing that happens, because we've got two high tides on opposite sides of the planet. So here's going to be our planet, it's going to be green.
That's sick.
Okay, and then we've got the water that's covering the surface of our planet in blue. If we didn't have the moon, it would be in like an even layer around our planet. But let's say we got the moon and it's over here, okay? This is not to scale at all. What happens is the water over here is pulled towards the moon. So like over here it gets shallower. We've got less water sort of in this zone. And over here it gets kind of bulged out.
Whoa.
Right? Again, not to scale. So our high tides are here because it's close to the moon. And then there's a second high tide over here because gravity is stronger with proximity. So here where we're really far away, the water over here, gravity can't pull on as strong. So we've got a high tide that's like on the far side of the planet because it's harder for gravity, for the moon's gravity to pull on this water than it is to pull on this water. And then on these sides, here and here, we have low tide.
What? No.
Yeah.
So when your planet spins either to the closest or the farthest point?
Yeah, it's like where the moon is what determines where the high tides are. That's why it changes over the course of the day, because the moon's in a different position relative to our planet.
Whoa.
Yeah, Karen?
Why does the other side have high tide too?
Gravity is weaker the farther away something is. So the opposite side of the planet is weaker because this water can't be pulled as well by the moon.
That's it.
That's why we got a high tide on the far side. Yeah, it's really weird and interesting. All right, any last questions?
That's it.
Okay, let's go ahead. We can stop that video.